My name is Rasmus Bro. I work at the University of Copenhagen in Denmark, and we have this series of Monday webinars, and we're very happy to have Tammy Calder here. Tammy Calder has been working for more than 20 years in Sandia Labs in California, but now she has her own company, mathsci.ai, and is doing both research and consulting, I guess. She's also the editor of a new science journal, the Journal of Mathematics, on Mathematics of Data Science, which is very relevant for us. But most of all, she's very skilled in tensor analysis, so I'm looking very much forward to hearing this talk, Tammy. Please go ahead.
Great. Well, hi, everybody. Thank you for hosting this today, Rasmus. I'm going to talk today about something called generalized CP. Maybe you can call CP as PARAFAC. It's tensor decomposition, and its utility for data analysis and mathematical challenges. If you have questions at any time during the talk, do feel free to post in the chat. I have it up on my screen, so hopefully I'll see it. And then also maybe you can, if you message Rasmus, he can interrupt, or you can even try to say something if that's possible. I'm not sure if it is. But feel free to interrupt with questions at any time. So let's see. So thanks to Rasmus for hosting me. I always want to give a couple of pointers. This work is a few years old, but I'm talking about it partly because it got sort of interrupted because of the pandemic, and partly because I would like to see, hear about more applications and try it out in more cases. So the papers were published in this journal that Rasmus talked about. It's my only paper that's been accepted to this journal so far. I'm very tough on myself. And then another paper that was in Science Review. And then this work was done while I was still at Sandia. All right, so I wanted to talk a little bit about this work in terms of the data science revolution. So the old way of having of thinking about things was often in terms of linear models. In this case, we'll talk about nonlinear models. This is not in any way surprising to y'all, because most of you have already thought about PARAFAC and tensors. One thing that we do typically in tensor models is minimize the least squares error. And today we're going to look at it from a different viewpoint of minimizing log likelihood, and that opens up some new avenues for changing up the objective function. And then the last thing, if we have time, and I think we should, in the old way, we thought about using deterministic algorithms to solve our problem. I'll talk a little bit about randomized algorithms. So before I get started, I want to kind of motivate things with an example application. So the application I'm going to look at is Chicago crime data. So Chicago makes data on criminal activity in the city that is collected by the police force, available for public download. And so these reports include a lot of information. We're using just the date, which also includes the time. Chicago itself is divided historically into 77 communities. I have those kind of outlined over to the right. There's one interesting little hole. Let's see if I can get my little laser pointer here. Oops. There is a hole right here that's not part of Chicago. Just when you see the maps later, that part will always be empty. And then there's different types of crime that they have. You can download this data directly, and I have done that and sort of turned it into a MATLAB-friendly data tensor that you can download at this URL. And there's two versions of the data set. I think they're both there, but if not, email me. One is just a 2019 data that has 244,000 incidents in it. And then another one that's 20 years of data that has over 7 million incidents. And I should credit that there's this formidable repository of large-scale sparse tensors called Frost. They had a version of this data set that sort of inspired me to go back and make a new version that goes a little bit further in time. So what does this data look like? So you can look at this data in different ways. You could think of it as just a community by crime data set over 2019. And so I have on the left a heat map, and it just shows the total number of crimes per neighborhood committed or reported, I should say, in 2019. And so you can see some communities have more crime, they're darker colored, and some have less. If you've ever flown into the airport there, this region is the Chicago O'Hare Airport. And then the types of crimes, I didn't include all crimes, I think it's just the top 11 crimes. So theft is by and large the biggest, then battery, then criminal damage, and the maximum here is 70,000 crimes. Now we could go further. We could look at what day in a year crimes happen. And so you can see, if we look at the total crimes per day, we see a big dip towards the end of January. I assume there was some sort of snowstorm that prevented much crime or crime reporting. It goes up in the summer when things are less cold. It's very nice and sunny and warm and longer days. And then you even see sort of peaks at the beginning of the months for some reason. I haven't fully, we'll talk about that a little bit later, but you see sort of a pattern in day. So then we have a three-way data set: the day, the community, the crime. And then we can go even further. So we can actually look a little bit at the hour of the day. And so we can see that there's even some differences in when during the day the crimes are reported. So this is 0 is midnight. So this is all the crimes between midnight and 1 to 2, and so on. You see 5 a.m. is sort of the lowest time for crimes. There's sort of a weird peak at noon. We'll talk a little bit more about that later. And then we see just sort of kind of different levels of crimes at each hour of the day. So when we put that all together, we have a 4-way tensor. And so if we look just at the 2019 data, we have a tensor which has 7.4 million entries. Not all of them are non-zero. Most of them are actually 0. There's 365 days, 24 hours a day, 77 communities, and 11 crime types. So we say that the IJKL entry of the data tensor is the number of crimes on day I, in hour J, in community K of type L. So that's the basic idea of our tensor. So there's 244,000 crime incidents that are in the database. And then when you sort of sum them up, some have happened in the same day, hour, community, and type. So there's 224,000 non-zeros. Most of them are ones, but a few are greater than 1. So a total of 3% of the tensor entries are non-zero. All right, any question on this motivating example before I go on?
All good, I think.
Great. All right, so now let's talk about tensor decomposition. So these are our nonlinear models. So we'll do a little warm up and talk about matrix decomposition. So you've seen probably versions of this, things like singular value decomposition, non-negative matrix factorization, and so on. So we have some data matrix that's m by n. We'll call that x. And so x will be our data all the time. Then we're going to say some model rank. We're just going to say that in advance, and then we'll call that R. And what we're going to compute is two things that we call factor matrices, A and B. So A is m by R and B is n by R, and those come from the sizes of the data and the model rank. And so what's important in these matrices is their columns. And so we're going to build up a model of X that's based on taking the columns of A and B and taking their matched outer product. So A1 outer product B1 plus A2 outer product B2, all the way up through AR outer product BR. So these have the same number of columns. And so we sum up those outer products, and that gives us our model tensor. So we can write it more efficiently. It's just M is A times B transpose. And we know because of the way we constructed M that its rank is no larger than R. And then when we go to tensors, we're going to use a different symbol for outer product and just AB transpose. We're going to write A, this circle operator B. And then we're going to sum that up over all the columns. So we have this subscript L to represent column L. And then if that's too much notation, no worries. You can just think of Mij is the sum that we show here from L equals goes 1 to R from AIL BJL. And then we want our X to be approximately equal to our M. All right, so that's what we're doing with tensors, with matrices. So now we can sort of just think of that same idea and just extend it to a multidimensional array. So I'll call this CP, tensor decomposition. So that can mean whatever you want it to mean. Some people call it canonical polyadic. It's also known as PARAFAC or canonical decomposition, PARAFAC or CANDECOMP. And then originally CP just came from PARAFAC, CANDECOMP, but now some folks have reverse engineered it to be canonical polyadic. And so this dates back to Hitchcock in 1927, Carroll and Chang in 1970, and Harshman in 1970. All right, so let's talk about the three-way case here. We have a data tensor that's M by N by P. And now we're going to have a model rank R, something we just say in advance as before. And then we'll do 3 factor matrices because it's a three-way tensor. And so they'll each have R columns, and then the number of rows will be determined by the corresponding size of the tensor. So M, N, and P, so we get MR, M by R, N by R, and P by R. And then we'll construct a model tensor M based on ABC. So the shorthand we'll use is M is just this double bracket ABC. And then because of the way we constructed it, it will also have rank less than or equal to R, even though I haven't told you what rank was. You just believe me on that. And then we're going to take outer products of matched columns again. So we're going to take the outer product of A1, B1, and C1. So we're doing outer product of 3 vectors and all the way up through R. And then we can write that in this outer product notation that we see here. Or element-wise, you could just think of Mijk as the sum from L equals 1 to R of AIL, BJL, or CKL. So one way that sometimes I think about this is that this is the ith row of A, and then Hadamard product or element-wise product with the jth row of B, and then element-wise product with the kth row of C, and then sum that up. And so we would like that X is approximately equal to M. So one thing is if X is M by N by P parameters, so that every entry has data, then we're kind of doing a data reduction. So now it's R times the sum of the sizes parameters. So this can be, if M, N, and P are fairly large, a significant reduction. So if we did a rank 100 factorization of a 100 by 100 by 100 tensor, this is sort of like a 33x memory reduction. And then we say this is multilinear because it's the model M is linear in A if we hold B and C fixed. It's linear in B if we hold A and C fixed, and so on. So once we, let me just also mention the D-way problem. So you can go up to D-ways. I don't know how to draw a D-way tensor, so I asked DeepAI's text-to-image generator to draw one for me. It looks mostly like a spider web, but suppose we have some tensor that's D-way, so N1 by N2 up through ND. Again, we choose a model rank. We have D factor matrices now, and so each of those has the number of rows specified by the dimension and of the tensor, and then they all still have R columns, where R is the rank. And then we'll do this outer product. I won't try to draw that, but our model tensor is based on all the factor matrices, taking the outer products of the corresponding rows, and then you can have this complicated formula for the entry. I only mention this because we have this 4-way tensor that is our Chicago data tensor, and we can go to any order D. And then as before, we want X to be approximately equal to our data tensor. Now we'll use a little bit of shorthand because you see there's a lot of subscripts here, I1, I2, ... ID. So instead we'll use this shorthand that X sub I is equal to M sub I, where this I means I1, I2, all the way up through ID, for example. And then again, we have this reduction in the data. So if we have N1 times N2 ... times ND parameters in our original data tensor, our D-way, our CP approximation has R times the sum of the dimensions. And so this can be a significant reduction. So if all the n's were equal, this is size n to the d. So it's exponential in n. And then this would be r times n times d. So it's a huge reduction in the number of parameters. So we think about our optimization problem. The usual thing we want to do is to take our difference between ijk and mij, square that difference, and then minimize that sum over all the entries. And then subject to our factor matrices having r columns. So that's our usual thing. We'll use the shorthand, summing over all entries of the tensor, xi minus mi squared is how we can write it, just sort of with this special notation. So that's our usual optimization problem. Any questions on that?
All good, I think.
Great. All right, so now let's talk about this optimization problem. So we're going to talk about minimizing the log likelihood. So we can think of a probabilistic interpretation of what we normally do with fitting PARAFAC. So we have our data tensor X, and we're trying to find a model M that's approximately equal to that. What we can think of is that our model plus some noise is equal to our data tensor. And so this is often what people say. They say each entry X of the tensor is equal to M plus white noise. And by that, I mean the white noise is normal distributed with mean 0 and standard deviation sigma. So this is kind of a common assumption in a lot of modeling problems. And so you can write that instead as each xi is actual normal distributed around mi with standard deviation sigma. And so we can maximize the likelihood of that. So we take to maximize the likelihood of X given model M. What this means is we're trying to maximize the product of all the probability distribution function evaluated at xi with parameter mi representing the mean mu of the normal distribution. And so we typically don't maximize the likelihood directly. We maximize the log likelihood, so that changes the product to a sum of the logs of these PDF functions evaluated at xi and mi. So what does this mean? So when you have a normal distributed variable, if X is normal distributed with mean mu and standard deviation sigma, its probability distribution function is given by this funky thing here, which is a bell curve. We talk about it's a bell curve centered at mu. And then we can sort of evaluate the probability that X is between A and B by integrating this PDF function from A to B. And so that's how the probability distribution function is used. And you can also use it in this minimizing the log likelihood. So we're assuming that xi is normal distributed with mean mi, so that's substituting in for the mu, and some constant mu or sigma for the standard deviation. We're assuming that's the same across all entries. Then we're going to maximize this log likelihood. So we're going to take log of this function here with mi equals mu and sigma constant. So we plug that in, we get this formula here. And so because we've taken the log, this means that we get rid of this exponent here, and then this sort of splits the fraction, it becomes a minus, and we get this sort of sum here. Now, sigma is constant, so we sort of can pull out this 2 sigma squared to the front of out of the summation, and so we're just left with xi minus mi squared, and then the second term actually ends up just being a constant. So we can just think of this as this transformation here. We're maximizing this. Oh, here's where our constants come from. And then we're maximizing this so we can minimize this thing where we just get rid of this negative sign, because we're going to go from maximizing to minimizing. And so we're minimizing this thing, which is our standard sum of squared errors. So you can do a probabilistic interpretation of what we normally do. And so the general statistical framework is that we want to maximize the likelihood of our model given a model that parameterizes a distribution. So we have some data tensor entry. We have some probability density function or probability mass function It doesn't have to be the one from the normal distribution. Then we have some parameter theta sub I that is describing the distribution. So in the last case, it was the mean was our natural parameter. And then we have some link between the model entry of our tensor and the natural parameter. And so we get to specify the link. The link will usually be the identity, but I think I'll show you, I can't remember. I think I showed you at least one example where it's something different. All right, so the statistical framework for the loss function then means that we take this setup. So we have some probability distribution function and a link function. And then we're going to maximize the likelihood. So we're going to take the maximum of the log of the probability distribution function, evaluate xi, and then whatever our mi turns into when we put it to the link. And then we're going to work with the negative log likelihood just to make our lives easier. So we're going to minimize some arbitrary f, which we'll figure out for each loss function. That is an affine transformation of the what we saw before. Any questions on that? I'll give you some examples which will hopefully bring it home. It's like, no, feel free to type any questions in the chat. All right, so now we'll talk about the what we're going to do when we have count data, which is what we have for our Chicago tensor. So suppose we assume that our data is Poisson distributed. So this means we observe data that's 0, 1, 2, it's sort of count data, and we have some parameter lambda, and lambda can be any positive real value. And so we have some probability mass function, which says the probability of observing x, given that our distribution parameter is lambda, is this funky formula we see here. So for example, if lambda was 5, then our distribution would be what we see here. So almost no chance of observing a 0, a little bit of chance of observing a 1, the highest chance of observing a 5, and so on. So that kind of looks not unlike a normal distribution. The only difference is it's discrete. So you can only have values that are integer. If we have x or lambda is 2.5, then things change a little bit, and we see sort of a distinct possibility of observing zeros. You can't observe anything less than 0. You can only observe positive or non-negative whole numbers. So our distribution would look like what we see here. If our lambda was 0.5, now our most frequent observation is going to be 0. See that about 60% of the time. Then 1's about 30% of the time, 2's about 10% of the time, and so on. And it tails off very quickly. And then, so that's sort of the different values you can get. And then we can write out the negative log of our probability mass function. So it comes out to this funky thing here. And then as we have x is approximately equal to m, we're going to have xi is Poisson with parameter mi. So each entry of the tensor x will have a different m. That comes from our multilinear model. And then we can write our objective function as we see here. We want to minimize m, this model, and then we drop off the constant term, which is the plus log x factorial, and we just get mi minus xi log mi when we plug in mi for lambda. And these are all with the mi is positive. And so if our data tensor has xi equals 5, what would be the best mi? So the best mi in this case would be mi equals 5. Now our model's constrained to be multilinear, so we won't get exactly 5, but that's what it's shooting for. If our data that we observe is 3, then the optimal value for lambda will be 3. If our data is a 1, the optimal lambda is 1. If our data is 0, the optimal lambda is 0. And the interesting thing here is this is just linear because our term with the log disappears when xi is 0. And so depending on what our data tensor is, the optimal mi will be different, and we can't just choose the optimal because our model is constrained to be multilinear. So that's for count data. What if we had binary data? So just 0, 1 data. So it could be this a coin flip, and this random variable is parameterized by some parameter rho, which is the probability of observing a 1. And so we write that as x is a Bernoulli random variable with likelihood rho, and our x is in 0, 1. And so our probability mass function that explains the distribution is rho to the x times 1 minus rho to the 1 minus x. And so if we take the negative log likelihood of that, we get this funky formula here, x times log rho plus 1 minus x times log 1 minus rho. And so we want our x to be approximately equal to m. What does that mean? Well, we have to link things. So here's a link that's other than the identity. We're going to say that the model will give us the odds, and the probability of rho, the probability rho is 20%. So if rho is 20, then our m will be 1/4. If rho is 50, then our odds will be 1. If rho is 80%, then our odds will be 4 to 1. And I see there's a question now. I'll stop in a second. And if our probability is 90%, we'll say that our odds are 10. All right, so it's a question. Thank you for the question. I didn't understand why we replaced lambda, the parameter, with mi, our approximated tensor data. Why not replace xi by mi? So yeah, that's a great question. It has to do with what we're trying to maximize, the log likelihood. And so we observe the xi, and then our prediction is based on the this m sub I replacing the lambda, and we each xi gets an individual mi. And so we're looking at if mi is the parameter. Let's see, that makes sense to go. I'm trying to think if I should go forward or back. Let me go forward. So if we have an observation 0 or 1, we're going to do something where we predict the odds. So I should note, we could just say that we'll let m be something between 0 and 1 and directly sort of predict x and try to do some least squares error. And people definitely do that. There's a couple problems. One, it's very hard to constrain m to be between 0 and 1. M is nonlinear. And so this becomes a nonlinear constraint that's very hard from an optimization point of view to enforce. Two, when you get things out, it's not necessarily that easy to interpret when you do it that way. So you sort of have a bunch of small non-negative. Typically, you would constrain your m to also be non-negative, and then it'd be all the entries between 0 and 1. It's just harder to interpret and much harder to compute. And so we sort of have this xi and then some mi that sort of match to it. And so mi is replacing the, I should go back to the, to this one. So the lambda I should replace this mi is replacing the lambda I because that's sort of predicting, that's sort of the closest thing to predicting xi. I'm not sure I'm answering your question. Can you maybe say some more? You got it? Okay. And you do have choices. There's actually other people that rather than mi would put in exponent of mi, and then mi can be from negative infinity to infinity. And you can actually try that. And we talk about that more in our paper. I have found that this choice usually works better with in terms of interpretability of data, but that's a subjective opinion. All right, so you can play this same game with Bernoulli, and then here's a neat thing where we do something different. So the formula is actually rho sub I, link is mi over 1 plus mi. So we plug that in, we'll say xi is Bernoulli with this connection to mi as we show here. And then you get this funky formula when you plug everything in, but it simplifies a little bit to this. So log of mi plus 1 minus xi log mi. And so it's interesting. You have two possible things you can observe, a 0 or a 1 in your data tensor. If you observe a 0, the best m sub I will actually be 0. If you observe a 1, then the best m sub I is actually plus infinity. And so because you're constrained, you won't really get either of those in practice. All right, so now if we think about our general optimization problem. So we have some f's. In this last case, the f, so the little f was this log mi plus 1 minus xi log mi. We have some f. We want to find our best model. subject to the rank less than or equal to R, which just means that we're going to have A, B, C with R columns, and our formula is given here. And we can compute the gradient of this using the chain rule. So it's kind of an ugly formula. Don't worry too much about this, but just know that we can compute the gradient with respect to all the parameters of our ABC matrix and compute that using chain rule pretty easily. So if we go back to this 2019 data from Chicago, we're going to use that Poisson loss function with a little itsy bitsy change, which is that our MIs, if we have a 0 value in the X and our MI is also 0, if we have a non-zero value in the X and our MI is 0, we'll take a log of 0, which we can't do. So we'll put in some small positive values that will never take the log of exactly 0. So in MATLAB, we'll just change the function ever so slightly with this plus 10 to the minus 10. It'll still be an enormous value if xi is non-zero and mi is 0, so it would work well enough from an optimization point of view. And then we can say mi is just non-negative rather than strictly positive. So we run this in MATLAB using a nonlinear constrained optimization solver called limited memory BFGS with bound constraints. We run each example rank. So we need to pick what rank we want to use. So we'll run a bunch of different ranks and we'll run each one 5 times. You can't really see it here, but if you sort of zoom in on these dots, you can see that there's actually 5 dots in each of those places. The interesting thing is it seems to converge always to the same solution for every run, which is a good sign. And then we'll pick somewhat arbitrarily a rank of 7 for our examples because it fits on the screen and things don't change much when you go to 8, 9, 10, or it doesn't. And there's some change that I like from going from 6 to 7. And if you have questions offline, I can show you the differences between those. All right, so when we do our decomposition, we get this, what I'm kind of showing here. So we have some Chicago crime data tensor that's actually 4-way here. And then we're going to take the sum of outer products of 4 vectors. So we have a date, the day of the year. So there's 365 entries here. That's one of the vectors. An hour of the day. So we see that next. The community where the crime occurred, the 77 different communities, and then the crime type. So each of these rows corresponds to one outer product in our sum for our model. And so just at this level, I'll just show you that these right 3 columns have all been normalized to size 1, and then all the weight of each component is in this date. And you can see as we go down, they get smaller and smaller because the overall weight of that component is less and less. And then you can see also there's differences in when during the day crimes occur. So these are sort of midday crimes. This third component shows a middle of the night crime. These are crimes that somehow peak around dinner time, and so on. So we'll zoom in a little bit on these. The community is hard to interpret here, so what I'm going to do is kind of go through each of these in a little more detail. So if we look at the first component, this is mostly theft and deceptive practice, and it's usually during the daytime. And this area that's highlighted here is a very touristy area of Chicago. And so I think this is just like pickpocketing and so on. And then this is happening all throughout the year. If we go to the second component, this is in a different part of town, and it's more violent crime, again, mostly during the day. And then we see, different patterns. You can't really see here, but if you, there's slight gray bars are the weekends. And so some of them we can see some correspondence, but these are mostly these things are actually peaking during the week. And then here's one that's really things that are happening kind of in the same general place, but the middle of the night. And then in this case, these are peaking on Friday nights. I don't really understand why, but if you see these peaks are right at these gray bars, and this is where a lot of this crime is happening. This is another one that is theft. This is narcotics. So I gave this talk a few months ago, and the grad students told me now they know where to buy drugs in Chicago. It peaks around, mid-morning and sort of around dinner time, and then throughout the year. And I will mention, and also during the week. I will mention that these are crime reports. So this could also just be when they're reporting these crimes and maybe has no correspondence with when they're actually happening. Then we see another thing that is just sort of general theft and various things sort of evenly spaced throughout the city, sort of the junk thing. And then here's another crime that peaks in the middle of the night and the touristy areas, theft and so on. This is usually also on the first night of the weekend. And then this is an interesting one because it peaks at midnight, 9 a.m. and noon. There's actually a big peak at the beginning, first day of each month. And then also if you zoom in on Mondays. And this is because people are reporting, these are difficult crimes to report, presumably, so deceptive practice and certain types of theft. And so what I think is happening is they're being reported on the first day of the month. And then there's an arbitrary time picked, but not a consistent arbitrary time. So sometimes it's midnight, sometimes it's 9 a.m., sometimes it's noon. So we found some interesting features that have more to do with the way the data is recorded than probably the actual data itself. But anybody who's worked with real data know that these things are pretty common. And usually the first thing in my experience that tensor decomposition finds for you is abnormalities in your data itself. Any questions on that?
I may have one or two. Did you think about splitting into, you know, like months or something or weeks?
I mean, you absolutely can. We've already split data two ways, which was day of the year and hour of the day. Month would be hard because they don't line up. You know, you have to have the same number of days per period. But we can definitely do week, and we've done that in other cases.
Right, because there seems to be a weekly periodicity, whatever that word in there. Yeah. Okay. Thanks.
Yeah, absolutely. And it's sort of, I think, an open question is, can you discover the right periodicity to use and the right way to break up time? But it definitely varies per data set. And you could even take the same data set and see different things depending on how you handle time.
Right. Makes sense. Thanks.
Mm-hmm. And then there's a question that came up in the chat. Using the quasi-Newtonian algorithm to solve the objective function, how can you ensure each mode except for time is normalized? So this is a great question. Where do we enforce the normalization? And so we actually don't, we enforce the normalization only at the very end. So it's really a post-processing step. During the optimization, we just we don't explicitly have weights at all. We just have the factor matrices and we let them do whatever they want. We have the option, I did not use it here, to add a little bit of regularization to keep the factors from going too large or too small in size. But we didn't even need it in this case. So I didn't use it because it's another parameter to pick. And then in post-processing, then we normalize things so that all the weight is in the first component. Does that answer the question? Great, thanks. All right, so then I'll spend the last few minutes just talking a little bit about stochastic gradient descent and bias sampling. So we talked about that. The data I showed you was from the 2019 Chicago crime data set. And so if we store that, it's only about a tiny fraction of a gigabyte. So I could do it on my iPhone. If I look at this 20-year data set, now we have 20 times more days, and then we get 41 times more entries into our data set. So the non-zeros have grown by a factor of 28 times in the tensor. And so we have a 2.4 gigabyte tensor if we store it as dense. We won't do that. We'll store it as sparse, but it's still a quarter gigabyte. And more importantly, when we do the computations with this tensor, we tend to form gradients, which actually do take 2.4 gigabytes. So that's a bit of a problem. And so if we look back at that gradient formula, we see that we have sort of the summation already tells us that probably it's good for random stochastic gradient descent. And so we can actually randomly sample across these IJK entries We can still compute a gradient, and it turns out it's much, much more efficient to compute the gradient this way, but I won't go into the details now, but just tell you that it's more efficient. And so where you have this gradient calculation that we're doing, and the way that I think of it is if we were to compute this thing explicitly, we'd have a dense tensor, which I'll call Y, which is just these pieces that we need to compute the gradients. So this tensor, you can think of it as that I take the derivative of that little f with respect to m, and I fill in this tensor Y with all of the values from this partial gradient. And so its total size is m by n by p. I'm going to just call that big N, just for comparison. So big N is the total number of entries in the tensor Y. And then we're going to instead just take a few entries of this tensor Y. That's what picking those IJKs for the stochastic gradient corresponds to. And then we're going to get some stochastic tensor Y. We're going to reweight those things so that in expectation, the sample tensor is equal to Y, and that the number of non-zeros in this stochastic version of Y is very small. So we'll call the number of non-zeros S. The number of samples is much less than or equal to the total size of the original tensor, but we've weighted things so that the expectation of this stochastic tensor is equal to Y. And so we're going to use stochastic gradient descent, but we're going to use a special version of it, the adaptive momentum stochastic gradient descent, or ADAM. And we could use regular stochastic gradient descent. It's just a little more sensitive to the choice of step length than ADAM. So ADAM's just sort of, usually you can just sort of run it and forget it, and it just sort of converges without too much tuning. All right, so now, we're going to create, oh, let's, we have a question. Can we apply this gradient? Oh, so for the question, the gradient optimization on tensor including complex values, not only real or binary. The general GCP, if you have a probability distribution for the complex values, it should work. I haven't really tried it. It's a great question. It would be interesting to try. So I'd be happy to chat later if you want to send an email or something. And if that doesn't answer it, maybe we can come back in a few minutes and see. So for the picking this Y, just few entries of Y, how can we actually pick those? And so that matters a lot from getting your stochastic gradient descent to actually converge. So you have to pick your entries so that you get everything equal in expectation. So one way you can do it is just pick entries at random. And so we'll define a variable SI tilde that is the number of times that you sampled entry I when you're just sampling uniformly with replacement. And then you can reweight your tensor, your entries of your tensor Y. You take the original value and you just sort of upscale them so that in expectation Y tilde is equal to Y. And so we can prove that, but I think I'm going to not go through the details of that right now. And the advantage of this is that you can choose your S to be pretty small, and the gradient is very cheap to evaluate. So it's R times little s versus R times this huge value and the number of entries in the tensor. And you can control S. And basically the bigger S is, typically the faster it will converge, but you can choose S small enough so that everything is very easy to fit in your memory of your iPhone or whatever you're calculating on, for example. The downside is that if the data tensor is sparse, when you're only picking a few non-zeros per gradient, most of those entries you pick will correspond to zeros rather than non-zeros. And actually all the information is in the non-zeros, and so that can be bad. And so there's a lot of theory to describe why that is. And so one piece of theory that I kind of like is by Needles, Schribo, and Ward, which says that these little f's that you're picking, the ones that have higher Lipschitz constant are going to be more valuable in fitting your function. And so what does that mean for us? So if you remember, we have these little functionals that we're optimizing with respect to M, and they depend on X. So our X is our fix, that's our data. And so if our data was 0, then we get this straight line here. And so this is really easy to optimize. And so this is sort of boring. It has a Lipschitz constant that's 0. And so you don't really need to think too much about this one. And then The others have Lipschitz constants that as you get close to the MI being 0, they explode. And so these are very important. So we need to include those in our, we need to include these more frequently in our samples, because those are where all the information is. So we were sort of looking at how to make this stochastic gradient descent go faster. If you don't, it will be guaranteed to work no matter what, but if you don't choose good samples, it would be very, 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 very slow. And so we want to choose something a little different, where we're going to sample zeros less frequently than non-zeros. So we can partition our data. We can partition it any way we like, in any arbitrary way. And so this sort of formulas I show here are for an arbitrary partition, where omega sub L is your Lth partition. And you can set how many samples you want from each partition. So we'll call it S sub L. And it's much smaller than the total number of entries in that partition. And then you can do sampling, and then you reweight so that things are equal in expectation. So what you can think of it is you divide your data into two groups, non-zeros and zeros, and then you build up a sample from those, sampling separately. Again, you can prove that everything is correct in expectation. There's some little nuances. Our non-zeros, we have an explicit list when we store a tensor as sparse, but our zeros, we don't actually store a list of all the zeros. We only know that what's a zero because it's not a non-zero. So we have to sort of sample and then check if it's a zero or not, and then reject. I'm not going to go through all those details, but happy to chat more offline on that. So now we have a way that can scale to much bigger data tensors. So if we go back to that 20-year data set, we can run that. And so here's a method that was developed previously, actually my group, that we call it CP alternating Poisson regression for running on large scale data. And so we can see that as we do I didn't say what the rank was here. I'll tell you on the next slide. But as we run that in time, we sort of see this convergence here, and it eventually converges to a solution. If we do the stochastic gradient descent and we take uniform samples using this add-on, we can see it converges more quickly. But one problem is it doesn't converge to the same Y value as this blue dots, the regular non-stochastic algorithm. So it converges fast, but it's not to the same answer. So that's not very satisfying. We could run it a lot longer. In theory, you would eventually get down to a better solution, but that's not, then we haven't won anything by being random. But if we use this stratified sampling, now we're making more progress with each stochastic gradient evaluation, and we get down to the same quality of solution, and we do it much faster. And so we're using 10,000 samples for each stochastic gradient that we compute here, and each dot here is an iteration of the method. So now we can look at data for 20 years. So here we have 20 years, a little hard to see what's going on here, but we see like some crimes went down in time of these 20 years, which could be reporting, could be new policing, who knows. We see some stuff that's sort of constant. We see stuff that goes up every summer. Certain crimes are more prevalent in the summer. It's very cold in Chicago in the winter. Another crime trend going down, some stuff sort of constant, and so on. I'll zoom in on a couple of these. Here's the crime that's going down. Narcotics crime reports are going down in this region. We saw they were still high in 2019. We see here we have the COVID year, so we see an interesting blip around COVID time. And then we have, again, the sort of standard traffic of crime that's in the tourist area of theft, usually during the daytime. And then we have middle of the night crime that is usually some battery. This is sort of violent kind of crime or criminal damage in this area over to the left. And this sort of peaks in the summer and in the middle of the night. And these are all the trends that are pretty consistent. Here's our funny one. This one actually peaks a lot at the beginning of each year. The smaller peaks at the beginning of each month. And it's some of those deceptive practice and thefts and stuff that we didn't have an exact time. Peak around midnight and noon and 9 a.m. as we saw even in the 2019 data. And then we saw some crime trends were going down. Sometimes things move around. So here's a crime trend that's going up. So this probably means that the location of the crime sort of moved, and so it got a new component. And then here's another one that's going down. And so I'll wrap up just to say that tensor decomposition is a multilinear model, so it's a much more interesting than some of the linear models that are out there. The loss function that you use can make a big difference in the result that you get. You can use any loss function you want in the generalized CP decomposition. So we talked today about using the standard normal sort of assumption corresponds to the standard way we do CP with least squares area. That's the Gaussian or normal distribution assumption. You can use a Poisson distribution for count data. You can use Bernoulli distributions for binary data, but you can use other things too. There's been past work by Sahoki and others on beta divergences. Those are pretty powerful in my experience. You can do Huber loss for binary data. That's very popular in machine learning. You can also just try to have a loss that depends on your empirical distribution if you have enough data. And then we ended by talking a little bit about randomized optimization to speed things up, especially for a very large problem, and how you might want to be smart in your sampling, but there's still much work to do and the best way to do that. And I'll stop there and take questions. Thanks.
Thank you so very much. Very interesting. Let me just say that I forgot to say that you are also the co-author of the Tensor Toolbox, which I guess most of what you talk about here is implemented in the toolbox.
Absolutely. Yep. Everything is in the Tensor Toolbox. And
So
there's also, yeah, thanks for posting the link. And there's also a C++ version. And there's very close, I mean, it sort of kind of exists, a C++ linking to Python version. So yeah.
That is nice. So if you guys haven't tried the Tensor Toolbox, I really urge you to go there. There's some really nice tools there. And the nice the object, the dataset object, the tensor object for holding the data and sort of, yeah, it's smarter than what MATLAB does, basically. Very nice. Any questions?
I see Ahe has his hand up.
Yeah, very nice, Tammy. We work on now a lot of microbiome data, and that is actually, it is either zero-inflated Poisson or zero-inflated negative binomial data.
Okay.
Do you think your methods can accommodate those kind of distributions?
I think
because
so.
they're not member of the exponential family. Huh? I noticed that your distributions are members of the exponential family, but those are not.
Right. I think I did in our paper, I think thanks to a question from you, actually, we do negative binomial. I have to go back and check. And I haven't done the zero inflated Poisson. That's really two parameters, but we should be able to make that work.
That would be quite nice, actually, because that is the type of distribution we struggle a lot with, actually. Yeah.
Oh, okay. Yeah, let's definitely talk about that. Perfect.
That could be, yeah, that could be very interesting to look at.
Yeah. Yeah.
Yeah, I'm making a note.
And there's a question about where to find the recorded version. Well, we're going to put it on our YouTube channel. I'll get the link. Just a minute. Oh, stop. Here we are. Let me show you.
What we see down here is actually.
Apologize for this, but here, this is the YouTube channel where we will post this in a day or two. So yeah. Tammy, can I ask you, if you did least squares on this, would it be dramatically different or similar? Do you have any idea?
Let's see. Do I have that as I don't have that as a hidden slide. It would be dramatic, pretty different, yeah.
Okay, yeah. I can, yeah, because you have many unique small events, or that would confuse the least squares.
Right, like there's not too many high counts that confuse the least squares, but it would have negative values, could maybe constrained to be non-negative. You'd kind of be chasing things down and like whack-a-mole.
Yeah.
You can do it, and you'll see signal, but it's just not as good and as clear and as interpretable. That's the interesting thing. And in the paper on this, we go through one example with neuro data where we look at a bunch of different loss functions. And depending on your situation, any could, depending on what you're trying to get out of it, they all potentially have merit. We used a prediction assessment. So we predicted some data that we held out and used that to choose the best one. I think we also show them visually and sort of stare at them and try to decide what you think is best.
Nice. Okay, I like that. I need a link to that. And there's a question.
Oh, how to show.
Can I have another question, Rasmus? Is that okay?
Yeah, it's perfectly fine.
Okay. Yeah, Tammy, we have been working a lot in our group lately with generalized linear models. So we have these link functions like log and log link and what have you. And what we stumbled across was that residual analysis is not straightforward. You have Pearson residuals, Anscombe residuals, deviant residuals. So how do you go about in your generalized CP models? Can you still look at residuals? How do you do that?
Oh yeah, no, residuals are much more complicated.
Yeah.
Okay,
so that holds also. Yeah. Okay. Yeah. Okay.
Okay. No more questions. Well, then I just want to thank you very much, Tammy. This was really, really interesting, and it could be fun to start collaborating on this.
Yeah, I really like to collaborate on the zero inflated stuff. That would be quite nice.
Yeah, that would be great. Let's definitely email about that.
Yeah, and if you solve the problem of the residuals, that would also be great, Tammy.
Well, maybe we'll think of something.